Hey everyone! In this video we're going to learn how to make a Karnaugh map given a truth table. So we're going to take the truth table pictured here, which has 3 inputs and 2 outputs, and we're going to make 2 Karnaugh maps, so one for each input. So in general, if you have a truth table that has one output, you're going to have one Karnaugh map, and if it has 2 outputs, you're going to have 2 Karnaugh maps. So you'll notice that if you're doing homework 3, you have 3 outputs, which means you're going to have 3 Karnaugh maps. Hopefully that clears up some confusion. So before we start learning how to make a Karnaugh map, we have to learn something called gray code. Now normally when you increment binary numbers, imagine that we have a 2-bit number. We would start with 0, 0, and then we would move to 0, 1, and then we go 1, 0, and then 1, 1. So we'd get 0, 1, 2, 3. But with gray code, we're only allowed to change one of these bits at a time. So this is, I'll write normal. And then I'm going to do gray code. With gray code, we can only change one bit at a time. So we'll start with 0, and then we'll go to 1, just like normal. But we can't just jump to 1, 0, because that involves changing both of these bits. So we change a 0 to a 1, and we change this 1 to a 0. So what we have to do instead is we have to skip to 3, and then we go back down to 2. So you'll notice that from step to step, from number to number, we're only changing one of the bits. And that's what we need to lay out our truth table, to lay out our Karnaugh map. So let's go ahead and draw the Karnaugh map for E, and we're going to just go ahead and draw. We have 8 output rows, and so what we're going to do is we're going to draw a 4x2 grid. So I'm going to go ahead and make it twice as wide as it needs to be on my graph paper. So we got 1, 2, 3, 4, 5, 6, 7, 8. And then we'll go ahead and do 4 squares tall. And then I'm going to go ahead and separate this. Now we could have also done a 2x4 grid, so it would have been like this but rotated. It doesn't really matter the way that you do it, as long as your labels match up. You'll see what I mean in a second. So we're going to go ahead and put our inputs up here, and it's sort of like a Punnett square. So I'm going to write AB, because this is the longer side, we write both of the inputs up here. And then I'm going to write C down here. So each of these columns here is going to represent one of these pairs of the values of A and B. So I'm going to go ahead and do our gray code again, so 0, 0. 0, 1, and then 1, 1, and then 1, 0. So for each of these groups of bits, each of these pairs of bits, they map to the value AB. So in this square right here, we know that A and B are both going to be 0. And then in this square, if we look at the header, we know that A is going to be 0 and B is going to be 1 because it's A, B. And then in this square, it'll be A and B are both 1, and then in this square, it'll be A is 1, B is 0. And for C, since it's just one input, we're still technically doing gray code, but it doesn't really look like that because we're just going to do 0 to 1, and that's completely valid gray code. And real quick, I don't really have room. I guess I can write it there. I'm going to go ahead and label this as E because we're going to do this output. You can only do one output per Karnaugh map. Now when we fill this in, a lot of people get confused about how these outputs map to these values, but it's actually pretty simple. So you'll notice that this is A and B and C. So we get 0, 0, 0. And if we go over here to our truth table, we find that the spot where A, B, and C are all zeros, the output is 1 for E. So we're just going to go ahead and write a 1 right in here. And then if we go down to this square right here, we get 0, 0, 1 for A, B, C. So we're going to get 0, 0, 1 in our truth table, which maps to 1 as well. And we're just going to keep doing this, and I'm not going to go ahead and go back and forth between these every time. My ink keeps coming off. Sorry about that. So I'm going to go ahead and just show you guys what the pattern ends up being. So for this, we're going to get the 0th index. So this is mapping to this number, or these numbers over here, because we get 0, 1, 2, 3, 4, 5, 6, 7 for our inputs, because we always label sequentially in binary for our inputs. So this maps to the 0th row in our truth table. and then this is going to map to the 1th row, or the first row, which is actually the second row in our truth table. And then we're going to get 2, 3, because we get 0, 1, 0, which is 2, and then 0, 1, 1, which is 3. But then, remember our gray code, we ended up switching these two. We were going 0, 1, 3, 2. So we end up going 0, 1, 2, 3, and then 4, 5, 6, 7. So these two columns end up getting switched. And if you were to do a 4x4, you would have gray code here and gray code here. You would notice that also these two rows get switched at the same time. But you always just follow the gray code. One thing that's nice about this entire process is that you don't really have to memorize how to draw any of this or how any of these numbers fill in, or you don't have to remember the pattern or anything. All you have to remember is gray code, and you have to know that this value 0, 0, 0 maps to A, B, C, which maps to 0, 0, 0 in our truth table, which then gives us this output. Anyway, we're going to go down the line in our truth table and fill in these values. So we get the 0 with index is 1, and then 1, and then another 1 up here, and then a 0, and then we skip over here for the next row to 4, so we get a 1, 0, and then 2 more zeros. And then let's go ahead and do F. So F is actually going to have a slightly simpler Karnaugh map. Let me give myself enough room this time. So we're going to do 2, 3, 4. So I'll do our labels like this. And keep in mind that these labels A, B, C for our variables, if this was like, say, oh, I don't know, like A1, A0, B1, and B0, then this would be A1, A0, B1, B0. So these aren't always A, B, C. They're whatever the names of your inputs are. Anyway, let's go ahead and do our gray code. So 0, 0, 0, 1, 1, 1, 1, 0. Don't forget that, or else your Karnaugh map is going to be wrong. And everything after your Karnaugh map, which you'll see what we're going to do next, will end up being wrong as well. So then we'll do 0, 1, and then we'll just go ahead and go down the line. So we'll look at our pattern here, 0, 1, 2, 3, 4, 5, 6, 7, and we'll just fill this in. So we get 0, 1, 2, 3 is 1, 1, 0, 0, 1, 1, 0, 0, and then we get another 1, 1, 0, 0. So 1, 1, 0, 0. So remember that pattern of kind of coming outside in. And I'm just going to go ahead and label this as F. Okay, great. We've made it super far at this point. And this is sort of the easy part of the Karnaugh map, unfortunately. So the next thing that we have to do is we have to identify what's called the prime implicants. So I'll go ahead and write that, prime implicant. And what an implicant is, like prime or otherwise, is just any element of the onset. So any of these elements where the value is 1 is considered an implicant. And a prime implicant is an implicant that can't be grown any larger. So as a quick illustration, if I have, imagine I have this layout for a Karnaugh map. So, you know, very generalized. I won't even write the variable names. This is one implicant, but we can grow implicants to be any power of 2 that we want. So we can take one implicant, if we were to like identify this, I'm not going to circle it because I'm about to circle a bunch of them, but if I were to circle this one, we could say, it has a few neighbors, and we can grow it into any rectangular shape that is a grouping of 1s that is a power of 2 in size. So we can take this 1 and we could group it as 2, or we could take all of these and group them as 4. And I'm going to go ahead and do that. So this right here is one of our prime implicants, this rectangular grouping of 4. So we can have a group of 1, we can have a group of 2, or we can have a group of 4. We can't have a group of 6 because that's not a power of 2. But we can have a grouping of 8. So when we go ahead and apply that to these Karnaugh maps up here, a pretty good sort of algorithm for identifying these is to find an implicant. So let's take this implicant 1, and then let's say, okay, can we pair this with any of its neighbors? So we have another 1 right here, and then if we were to take that grouping of 2 and try to grow it, we can't, because there's a 1 right here, but we can't have a grouping of 3 because that's not a power of 2, and it's also not rectangular. So what we're going to do is we're just going to circle this grouping, and that's one of our prime implicants right there. Now, one special thing about a Karnaugh map is that it's kind of like a Pac-Man game, or any of those kind of classic arcade games where you can wrap around the side. So this 1 right here also can form a prime implicant with this one. So the way that we usually denote that is we group them like this, and it's generally understood that this sort of outward-facing grouping means that these two are grouped together. And we have this one straggler left, so I'm going to go ahead and circle that one. I wish I had 3 different colors, but you can sort of see we have this grouping of 2 1s right here, and we have this grouping of these 2 1s, and we have this grouping of these 2 1s. Now, imagine if we had, well, it doesn't really apply for a 4x2, but if we had a 4x4, we would also be able to wrap around the edges this way. So if we had a 1 up here and then a 1 all the way down here, if it was a 4x4, we'd be able to wrap around the edges this way. But you can't wrap diagonally, you can just wrap left and right. Just always think Pac-Man, and you'll get it right every time. Now let's go ahead and we'll do F. So this one is kind of tricky. It's one of the examples on the slides, I'm pretty sure, if you're one of the students at UCF who's taking the course ITA. And if we take this 1, we can grow it to be paired with its neighbor down here. But remember that we can also wrap around the edges. But this counts as a rectangle if I group all 4 of these together. So I'm going to go ahead and do that. So we have this grouping of 4. Alright, now we've identified our prime implicants, and now the real fun begins. What we have to do is we have to find the minimal form based on these prime implicants. So first thing we have to do is we have to make some observations about this Karnaugh map, or both of these Karnaugh maps. And I'm going to go ahead and just do this with one, like one of the Karnaugh maps. And the first thing we have to do is we have to find different regions where A, B, and C are asserted. So if we look at these columns up here, remember that these columns, each of them map to pairings of A and B. So in this column, A and B are deasserted, and in this column, only B is asserted. In this column, both are asserted, and in this column, only A is asserted. If we want to find the region where A is asserted, we just have to look at the left bit of each of these columns, and we can see that the left bit is 1 in both of these columns. So I'll take A, and then I'm just going to draw a little outline here. So we know that in this region here, these right 4 elements, A is asserted, and then in all the other ones, A is deasserted. So there's kind of like an implied A naught up here. Now we also have to find B. So if we look at B, it's the second bit of these columns, and we see that B is asserted in these 2 middle rows down here. So I could write it up here, but I'm going to write it down here just to kind of declutter things. So in these 2 columns, B is asserted because these second bits are 1. You'll notice that we don't have any elements of the onset that are inside of the area where B is asserted. Oh, sorry, this should be over here. Oops, just ignore that line. It's just a little spider with its web. There we go. Okay. And then the region where C is asserted is pretty obvious because C is 0 here and it's 1 here. So we know that all of these are going to be where C is asserted. And the same goes for this Karnaugh map. I don't really have enough space. I'll try to fill it in here. So here, this is the region where A is asserted. This is the region where B is asserted. I really don't want this to be confused with the other Karnaugh map. And then here is the region where C is asserted. If that makes sense. Okay. Now, I'm going to go ahead and start writing over here, but we're still going to be looking at these Karnaugh maps. And we're going to take these implicants that we just found, and we're going to look at the regions that we just identified, and we're going to use it to find the minimal form. So ultimately, the purpose of these Karnaugh maps is to find the minimal form, so the minimal function that can be used to describe this particular set of outputs. So what we're going to do is we're going to say E equals, it's not MC squared, and we're going to have f equals, and we're going to fill these in. This is generally the hardest part to wrap your mind around with Karnaugh maps, but just stick through it and we'll be fine. So we have to take each implicant at a time. If you remember sum of products form, this is sort of like that, where we have, like A, B plus, C, D naught plus whatever. We're going to follow that general form. So each implicant is going to map to each term here. So for E, we have 3 implicants. We have this grouping of ones, this grouping of ones, and this grouping of ones. And it's going to map to 3 terms. So let's go ahead and do that. So the first implicant I'm going to focus on, let's see, what's the easiest one first? I guess it would be these two. So these 2 ones, they're circled right here. If we look at the regions in which they lie, we can see that it's only in the region where A is asserted. So remember, if you look up here, A is asserted only in these right 4 elements. This implicant right here is entirely outside of A. So we know that we're going to have A naught in our term, because both of these ones are outside of the region where A is asserted. And then if we look at B, one of our elements is inside of the region where B is asserted, because remember, B is asserted inside these 4 middle pieces, or these 4 middle areas. And this one is outside of where B is asserted. Hey guys, sorry about that. My camera decided to shut off randomly while I was recording. So I'm going to go ahead and try to pick up where I think the camera turned off. So if I'm correct, we had just written down A naught as part of our term. And the next variable that we have to identify is B. So if we look at B, B is asserted in these 4 regions right here, so these 4 elements, and our prime implicant crosses over this region where B is asserted, and it's partially in the region where B is deasserted. So what this means is that we can completely leave B out of our equation, because we have B or B naught, which just cancels to true. So any variable ORed with any variable's inverse is true. So if we have, like, say that B is true, that would give us true or false, and that equals true. Or we could have false or true, which equals true. So we leave out B. And then C is sort of easy to determine. We have this prime implicant, and it's only in the region where C is deasserted. So that's an easy one. Okay, so we've gotten this term out of the way. Then we'll write a plus sign, and then we have to do the next term. So I'm going to go ahead and do this prime implicant right here. And what we're going to do is we're first going to identify A. So these 2 ones are entirely outside of the region where A is asserted. So I'm going to write A naught. They're completely outside of the region where B is asserted, so they're in this region right here where B is deasserted. B is also deasserted over here. So I'm going to write B naught. And it crosses over the region where C is asserted, because remember, C is asserted only along this bottom row, but we have our implicant is here and here, so we're going to completely leave out C, just like we left out B in the previous one. Alright, so we got that term down. And lastly, we have this implicant right here, which is this one and this one. So the way that we determine that is we look at A, and we see that this one is within the region where A is asserted, and this one is outside the region, so we're going to leave A out, just like we left out B, and just like we left out C here. So we're going to leave out A. It's entirely outside of the region where B is asserted. So this one is outside of B, this one is outside of B, so we're going to write B naught. And it's entirely outside of the region where C is asserted. So C is asserted here, this one is not in here, and this one is also not in here. So we're going to write C naught. And that's it for E. We're done with that. So this is the minimal form. If you did proof by rewrite successfully in homework 2, you can't apply that to this. This is the smallest form that you can get. It might not necessarily be the shortest function, but it's the smallest form that you can get only using 2 levels of logic gates, and this is the actual algorithm that's used when trying to make the smallest and most efficient circuits possible. So that's pretty cool. Now let's go and do it for F, and then we'll be almost done. We just have to do a gate diagram, and then we can wrap things up. So F is a much easier much easier minimal form than E because we only have one prime implicant. We have this giant one right here. And it's actually super simple. So if we look at A, it's inside of A here, and it's outside of A here. Because remember, A is these right four. You can tell by our little drawing here. So it's inside and outside of A, so we're going to leave out A. It's entirely outside of B, so it's these two right here. So we're going to go ahead and write B naught. And it crosses over the region where C is asserted because this one is outside of C, this one is inside, this one is outside, and this one is inside, so we're going to leave out C. So f as a function is just B naught, and you can confirm that by looking here. So f is only asserted when B is deasserted. So it's basically just B naught. And that's sort of the beauty of the Karnaugh map, is that we've taken this arbitrary function and we've reduced it to something as simple as one term being inverted. So that's pretty cool. The next thing that we have to do is make a gate diagram. So I'm going to go ahead and sort of shift things around, and we can ignore everything up here now except for these functions to draw our gate diagram. Alright, we've shifted our paper down a little bit, or shifted it up rather. So to draw our gate diagram, we're going to have two functions. We're going to have two outputs. So a clean way to do it, in your homework 3 you'll have 3 outputs, but you can easily scale this up. We're going to go ahead and draw our 3 inputs, and we're going to put some space in between them. So we're going to do A, B, and C. And I'm just going to go ahead and draw lines down these. And as long as they're reasonably long, you should be fine. You can always extend them later. And it's just going to be 3 long vertical lines. And then branching off of each of these, we're going to draw some inverters, also known as NOT gates. So now we have 6 signal lines. These are for A, B, and C, and then their complements are here, so we have A naught, B naught, and C naught. So I'm going to go ahead and label those real quick so that we don't forget them. So I'm going to draw them down here. So we have A naught, B, B naught, C, and C naught. So this is super convenient. We have to implement E and F, and all we have to do is we're going to take, this is 3 outputs that are ANDed together being ORed together. So the first thing I'm going to do is I'm going to look at this term right here. So we're going to have A naught, C naught. So I'm just going to draw a little bubble here. So I'll do A naught, because this is the inverted A, so we have our A naught line. And I'm going to take our C naught line. I'm just going to draw a wire here leading into an AND gate. So remember, this is A naught and C naught. So now we have our A naught and C naught term. I'm going to do the same thing for A naught and B naught. So I'm going to circle A naught, circle B naught. Draw these together. And then I'm going to take B naught and C naught. Now, this may look hard to read at first because we have overlapping wires, but trust me, it's much better than a spaghettified mess of wires and stuff, because it's just a consistent format, and you know that if you do it this way, it's going to look the same way every time, especially if you do the Karnaugh map in a consistent manner. Your terms might be in different orders, but that's fine. Okay, so we've got E almost done. We notice that these are being ORed together, all of these 3 terms, so I'm going to go ahead and draw an OR gate. By the way, the shape of the diagram isn't that important. If you're ever unsure, you can just go ahead and literally write and or, and the label will take precedence over the shape of the diagram. If for some reason you can't remember, don't worry about it. Just write the name and we'll understand what you mean as graders. For YouTubers who are just watching this for fun, then, you know, you do you. Okay. So we're going to have a 3 fan-in OR gate. So this isn't traditionally used in real circuitry. I mean, it might be. 3 fan-in OR gates are more expensive to build, but they are faster because it's 1 level of gates. So it's doing this instead of having, you know, A, B, C. So this is A or B or C. This is cheaper to build, but it's also slower because you have these two levels of gates that the signals have to propagate through. But anyway, that's too much detail. You can draw as many fan-ins to your OR gates as you want. On homework 3, I know for a fact that you're going to have an OR gate that has many fan-ins, so just don't worry about it. And we're done with E, so that's awesome. So there's E. And then F is extremely simple. We don't even need any gates for F because it's just B naught. So I'll go ahead and do this. I'll circle B naught, draw it all the way over here. And there's F. And we're done. So you guys, today you've learned how, and you can't see it, but I'm going to point just for fun. You've learned how to take a truth table that's been defined. You've learned how to do gray code. So I'm going to go ahead and just kind of make a bullet list of everything that you should make sure that you remember from this. So truth table, gray code, Karnaugh map, prime implicants, which kind of go hand in hand with Karnaugh maps, and lastly, making a gate diagram. Now, if you're a CDA student, you might want to keep watching, but if not, this doesn't really apply to you. For homework 3, instead of having defined inputs in a truth table for you, the only sort of conceptual jump from what we just did to your homework is figuring out how those two inputs, A1 and A0 and B1 and B0, get added together to make C2, C1, and C3. So for your homework, you're going to have 3 outputs like this, and you're going to have many more gates because the functions are a little bit more complicated. The second Karnaugh map is just kind of a nightmare to make the formula for. I specifically chose functions that would have clean gate diagrams and clean Karnaugh maps. So you won't be so lucky with an adder because it's not really a contrived example. So anyway, good luck. If you need help, I can always be contacted on web courses, assuming you're not watching this long in the future and I've graduated or whatever. And Mariah is also available to contact. So don't hesitate to reach out for help from us at any time. Thanks for watching.